everyone, and welcome to the part 3 video for Module 9, Dynamics, Work, and Energy. In this video, I'll explain about the goals, basic theory, and data and processing for this module, and also the general report format for the basic physics practice. So first, the goals of this experiment are to determine the magnitude of energy change in the system and to determine the spring constant using the concept of work and energy. Next up is the basic theory, starting with dynamics and Newton's law of motion. So dynamics is a physical concept which not only explains how's the motion of an object, but also what caused the motion, which in this case is a force working to the object. The principle of dynamics is the 3 Newton's law of motion. The first law explains the case where there were no force given to the system, or the total of force, or we could also say the resultant, is 0. In this case, then the system will tend to keep its current state, which is either stay at rest or keep its motion at a constant velocity. The second law states that if a force F works on a system at a particular direction, then the system will accelerate by A at the exact same direction. The magnitude of acceleration depends on the ratio of proportionality, which is m, the mass of the system. Therefore, we could write the second law mathematically as sigma F equals m times A. Lastly, the third law states that an interaction between two systems will generate forces from both systems, one to each other, in an opposing direction. Well, we could say this as a pair of action and reaction forces. The formulation mathematically was given as follows, which is F12 equals minus F21. Here are several forces which we might observe in this experiment. First is spring force, which is exerted by a spring of a constant K if it was being stretched or compressed by delta x from its equilibrium. Therefore, there will be produced a spring force of F spring equals minus K delta x, in which this minus sign signifies that the spring force direction is the opposite of the displacement direction. Secondly, the gravitational force, which is done by the Earth to attract every object to the center of the Earth. The formulation for this force was Fg equals m times g, in which this g serves for gravitational acceleration. Third was the normal force, which is generated by the interaction of a system and the surface it is placed on. Its magnitude will always be the same as the total force working on a direction perpendicular to the surface, except that its direction is the opposite. And lastly is friction force, which is generated by the interaction of the system and the surface in case the system is moving. Generally, the magnitude of friction force was given as F equals to mu times n, in which mu was the friction coefficient and n is the magnitude of the normal force. Next up is the free body diagram. This figure shows a free body diagram of an object with mass m placed on a rough inclined plane with an angle of theta. So free body diagram analysis is commonly done by splitting each of these forces into its directional components x and y. The direction of x and y can be determined freely. However, in order to simplify our analysis, we usually take the x-axis always parallel to the surface observed and the y-axis perpendicular to the surface. Next is the theorem of work and energy. The concept of energy can be defined as work done by a certain force, say F, so that the system moves as far as dr. Therefore, we can define work done by this force as Wf equals integral F dot dr. Now, if we make an assumption that this force is always constant, then by further mathematical derivation, we would obtain the following equation, which shows that the total work done by the force F is equal to the change in kinetic energy. The resultant of force working on an object or system consists of conservative force, where the work value doesn't rely on its strength, and non-conservative force, whose nature is the opposite. Now, the total work done consists of those done by conservative forces and non-conservative forces. Therefore, we can obtain the following equation. Conservative work itself can be defined as the change in potential energy of the object or the system. With that being said, if there were no non-conservative work, then we could define the theorem of work and energy as follows, which shows that the change in potential energy is exactly the same as the change in kinetic energy. However, both of them has an opposing sign. The gravitational potential energy is defined as delta EPG equals mg delta h, in which delta h here is the change in the object's height. In other side, the spring potential energy was formulated as follows, which is EP spring equals half times k times delta x squared. Next up is the data and processing for this module, starting with experiment 1, which we will study the relationship between spring potential energy and kinetic energy. Before we start the experiment, we have to measure the mass of each element that will be used in the system, including crane, lattice cover board, and the 4 additional loads. We'll use a digital scale which gives us the mass measurement result in gram, and it is convenient for us to convert this value to the unit of kilogram. Next, for the data collection, we will have 5 variations of mass here. However, I only show you 3 of them as the sample. For each of these variations, we calculate the total mass of the system from the previous data obtained. Then, from each different delta x, which is the change in spring's length, we obtain V1, V2, and V3, each as the 3rd, 4th, and 5th data shown in LogRapro by the PC. And then, we take the average of these 3 velocity values as V bar. And then, we calculate delta x squared and also delta Ek, or change in kinetic energy, whose formula is a half times m times V bar squared. Now, after all of this data has been collected, we do a linear regression with the x-axis of delta x squared and the y-axis of delta Ek, so that we obtain each a graph for every variation of mass. Here, we also obtain the linear regression equation, in which here the important part was the gradient. As you see here, the equation of regression here is delta Ek equals m times delta x squared plus c. However, if we count it the same as delta Ep, or the potential energy of the spring, then we could realize that the gradient is just half of the spring constant value, so that the spring constant value can be obtained simply by doubling the gradient value obtained. Therefore, we could have the following data here in table 3. Next, in the second experiment, we will study the relationship between spring potential energy and gravitational potential energy. We are no longer using lattice as an element because we are no longer using photogate as a sensor, but instead, we are relying on our direct vision from the eye. As previously, we calculate the total mass of the system according to the elements used, and then for each delta x, we obtain S top, which is the highest position that the train could achieve before it starts to wend downwards off the rail. And then we calculate delta S, which is the absolute margin between S top and S initial. And then we also measure H top, which is the height of the S top point relative to the ground. And finally, we could also obtain delta H as the absolute margin between H top and H initial. And then we also calculate delta x squared and delta Ep, or the change in potential energy, in which formulated as m times g times delta h, in which g was the reference value of gravitational acceleration. Here in LFD, we are using the value of 9.81 meter per second squared. And then, as what we done in the previous experiment, we do a linear regression, still with delta x squared as x-axis, however now delta Ep as the y-axis. Therefore, we will have this graph for each variation of mass, for a total of 5 graphs. Now the equation of this linear regression is delta EP equals m delta x squared plus c, in which if we count this equal to the spring potential energy, then, as was previously obtained, we knew that the spring constant obtained was just the double of the gradient value. So we could obtain the following data in table 5.